At this point, you should have read all of chapter 16. You should have done the problems I assigned from chapter 16. You should have attempted some of the problems from the AP problem sheet that I gave you. And if you haven't already started reading chapter 17, you need to do that. Tomorrow we're going to do a lab, and I know that there are a few of you who are going to be gone tomorrow. It's going to be your job to make up that lab ASAP. So you could do it after school today, or you could, I guess you can't, if you're going to Springfield, you can't do it after school today. Or you could try to find time to do it on Monday. This lab, which the rest of us are going to do tomorrow, takes the whole 2 periods to get done. So we're going to have to come in, be ready to go, and work diligently through the period if you're going to get through the whole thing. It's related to concepts from chapter 17. And we'll come back on Monday and we'll hit 17 even harder than what we have now. I hope that by the end of the period, you'll be armed with most of what you need to make a stab at the rest of the problems on the sheet. So I gave you a list on the email of problems that you ought to be able to already do. And after today, the vast majority of the rest of them you ought to be able to do as well to follow what we're doing.
How many people are going to be here?
1, 2, 3. So I would recommend that you 3 become a lab group and figure out how you're going to get in on, I guess, Monday. Because you're leaving like 3:45 or something today?
Yeah.
Did you want to try to, after class today, start it? No?
I mean, if it's
I guess not.
we want to print out our.
Are you guys done with your case?
No.
So I understand. So where are you at this point? Hopefully you have a sense of how to calculate the electrostatic force between charged particles. And we have an equation that allows us to determine the magnitude of that force, but we also need to be able to calculate the direction of that force. And that is a function of understanding what charges do when they interact, and this idea of like charges repel and then like charges attract. Secondly, we defined the concept of the electric field, and the magnitude of the strength of an electric field is the force per unit charge. So it's defined in very much the same way that we define the strength of a gravitational field. And those are the primary equations that you have to be able to function with in chapter 16. Now, there's a third equation that you probably made use of, but it's a function of putting those 2 together and calculating the electric field due to a point charge. And the resulting equation, which you need to put these 2 together at least the first time you do, is going to be that force, K, Q1, Q2, over R squared, divided by, and what are we dividing by? Whichever charge you use to test the strength of the electric field, which is one of these. If you're finding the electric field at a point due to charge 1, then charge 2 is your test charge. That goes away, and you get that the electric field is equal to the Coulomb's law constant times the charge creating the field divided by the square of the distance from that charge to the point in question. And I think everything I gave you from the textbook and everything from the AP problems that I put on that list can be done in terms of the quantitative parts. That's pretty much all you need, other than physics that you've already known how to do. You also need to know how to determine the direction of an electric field. How do you determine that?
Which way a positive charge, whether a positive charge be repelled or attracted.
I like the way you started the other time better. The direction of?
The direction of a positive test charge would accelerate.
Would be force. The direction of the force on the positive charge placed in the field. Okay. Now, given that, this is going to require you to draw a little bit on things you did freshman year with Castle, but consider these to be 2 metal plates that are separated, they're parallel and they're separated by a certain distance, And we're going to hook them up to this thing. What is this the symbol for? Battery, or actually a cell. We're going to use it as a battery in this class and just give it a particular potential difference. What's going to happen to these plates if you connect the cell to the plates?
Become charged.
Okay, why are they going to become charged?
Everything is conductor, and the pressure in one cell that's connected to the plate will equalize with the pressure on the plate.
Exactly. Both plates are going to, charge is going to flow between the battery and each plate until each plate is at the same electric pressure, or what we're going to start calling today electric potential, as that particular electrode or terminal of the battery. In Castle terms, we would have said this guy was at higher than normal pressure, this one's at lower than normal pressure, so this plate is going to push charge onto this plate until it reaches the same pressure as it, and it would end up with a net more than the normal amount of charge and therefore a high pressure. Electrostatically, you would say this guy ends up with an excess of positive charge on it. Again, in Castle terms, this terminal is at lower than the normal pressure. This plate being at normal pressure, this is at a higher pressure than that, so it's going to push charge off of it so that it's going to end up with less than the normal amount of charge and at lower pressure than it started with, and that will continue until this pressure matches that pressure. Result, we have two oppositely charged plates. Yes?
Positive and negative, is it, I mean, I guess before I was thinking about it like it's all relative, like something positive it has more of a certain type, but it's not because there's electrons and
Right.
there's protons.
So our Castle model only talked about there being one kind of charge. And what we would now call uncharged or neutral plates, in the Castle model just had the normal amount of charge on them at the so-called normal pressure. And we either added charge to the same space and got higher than normal pressure, or took charge from that space and ended up with lower than the normal pressure. But once we have this other two-charge model, then it's a little bit different. And how it's different is that a neutral plate, instead of having the normal amount of charge, has equal amounts of the two kinds of charge, right? If we understand that conductors, we know enough about atomic structure to know that conductors, solid conductors, only allow the movement of negative charges, then how would you re-explain this? Not in Castle terms, but using electrostatic ideas.
The negatives flow off the plate and into the battery.
Well, what it makes, so this guy has a net, has a positive charge, this guy has a negative charge. This is going to attract negative charges off of this plate, right? As you lose negative charges from this plate, if it was originally neutral, what's going to happen to that? It ends up with a net positive. This guy was neutral, this guy was negative, so what does it do?
Attract the positives.
Yeah, except the positives can't move.
Oh.
So it pushes negative charge onto this until, again, this pressure matches that pressure. What kind of electric field do you get as a result?
Yeah.
Okay, well, it turns out that it does point down. How do you know that? You put a positive charge anywhere in this vicinity, and we get pushed away from the positively charged plate and attracted to the negatively charged plate, so it's going to get pushed down. It turns out this arrangement is a very convenient arrangement for creating a uniform electric field. And it's fairly uniform as long as you stay near the center of this area. As you get to the edges, for reasons you can probably explain, the field has a tendency to fringe out a little bit at the edges. Now, today we're going to be talking about electrical potential and electrical potential difference. But we're going to try to build the concept from the concept of gravitational potential and gravitational potential difference. Now, where does the term potential come in when you've talked about gravity in the past? Energy. Specifically, gravitational potential energy. And how have you